Hi, good afternoon, and welcome to the National Science Week Expo Nanotechnology, organized by MOSTI NanoCat and University Malaya. And in this section, we are very delighted to have Dr. Zaira Zaman Chahuli, who is currently a senior lecturer in Nanotechnology and Catalysis Research Center, NanoCat, University Malaya. Uh, Allow me to introduce the speaker today. She received her PhD in Environmental and Analytical Chemistry from University Malaya in year 2013. Dr. Zaira's expertise is waste bioremediation, quality control of river water, pollutant detection, removal and management, waste management, and its impact in circular bioeconomy. She has contributed more than 150 papers in ISI and Scopus top-ranking journals, and she has a H index of 30. At present, she is guiding 12 PhD and 11 Master of Philosophy scholars. She is also the principal investigator of several prestigious international and industrial grants, which amount exceeding Ringgit Malaysia 7 millions. In these coming sections, Dr. Zaira is going to demonstrate wastewater treatment using nanocomposite materials by a column-based reactor system. Dr. Zaira, the floor is yours.
Thank you. A very good day to you all. Assalamu alaikum. Bismillahir Rahmanir Rahim. First of all, I will show my deep gratitude, express my deep gratitude to give me this honor and give me the floor to discuss about this issue. Today, my topic is real-time demonstration of wastewater treatment using nanocomposite materials via column batch reactor system. If we follow the name, here we can see that I have used the word nanocomposite as well as column batch reactor, because wastewater treatment is not a simple scenario. It depends on what type of waste we are dealing, what type of industrial wastewater we are dealing, or municipal wastewater we are dealing, or we are dealing only surface water, that is river water or groundwater. So that's why, based on the contaminant type, pollutant type, that means pollutant type, source of water, from where it is coming, and mother source for pollutant, is it industrial source or municipal source or ground source? Based on that, our water treatment technology will varies a lot, and then the nanocomposite will come to its use. We can use nanocomposite or microcomposite based on the type of water and the pollutant we are treating. Let us see what we are going to present today. Why water treatment is so important? Because there is a term today, water scarcity. Water scarcity means fresh available water which we can use for consumption purposes. We have a lot of water in the earth. Later on in my slide I am showing. But what happened? How much fresh water we have, how much we can consume, how much we can use it as drinking water, or how much we can use for household work, let's say cloth washing and other works also. So that is why water scarcity terms comes. So already there is water scarcity in the earth. If there is pollution also for the remaining less amount of water, then the scenario is really very damaging and alarming also. So we have to take care of it. It is really a social economical challenge for any of the country. That's why water scarcity and water pollution, these two terms are going side by side. And there comes another term, water treatment or purification. So that's why water treatment or purification is a big area, as I mentioned earlier, based on the pollutant type, source of pollutant material, source of industrial waste, the pollution prevention method will be different, or sometimes it can be combination of method also. Only single method cannot deal with the all types of pollutant. If we see 70% of Earth's water, Earth is water, but unfortunately 3% is only fresh water, because others are all salty water. That means seawater. So we need desalination. It is a kind of water treatment also. So our lab in NanoCat, we are doing desalination process also by using the membrane, nanomembrane or nanocomposite membrane. We are using that. So this is desalination is going on also, and the small amount of fresh water available, that is the 3% of fresh water, that one is also not also in different state, such as 79% is glacial, that is ice, 20% is groundwater, which is also some cases contaminated by some of the heavy metal, let's say arsenic maximum cases, and 1% is surface water in river, lakes, and other places. Even surface water, which is free flowing water, river, lakes, those are also not free from pollution, because we have industrialization. We are now in the at the age of industrialization. So what happened due to this industrial expansion, lot of pollutants are coming to the surface water also. And groundwater, most of the contaminant can come from anthropogenic sources, or from earth crust itself also some of the heavy metal can come out and make the water contaminant. To some places we have seen, especially in Southeast Asian region, let's say India side, we have seen the groundwater is mostly polluted by arsenic, or to some extent lead or other heavy metals. These are naturally coming from the earth, or those water are sometimes hard water, they have lot of alkaline earth material, that's why those waters are very difficult to use for household purposes. We cannot the soap will not have the feather on that type of water. We need soft water. Here I should mention that water is two types, soft and hard water. So we need soft water for our consumption, and of course drinking purpose also, right? So if we see that we have the drinking water which is clean, we call it potable water, and we need this potable water to be treated. We need it to be purified. Not only purified, we have to not only purified and free from chemical contaminant, we have to make it free from biological contaminant also, because water has physical, chemical, and biological, three types of contaminant which we have to dealt with. That's why water treatment process is a complex step. That's why I mentioned earlier also, it can be a combination of step. Only one single step cannot treat the water up to a greater scale. So this is the societal challenge, water scarcity. Different reasons these are happening. Let's say monsoon failure, industrialization, climate change significantly reduce the fresh water resources and expected to increase in future also. The main sources of water scarcity is pollution. Number one is pollution, because we have very less fresh water, only 3%, as I have shown earlier. But if there is pollution presenting, then pollution is present there, we cannot use that water. So this is the first option, pollution. Pollution is the main source of water scarcity. This one can come to the surface water also, this one can be in the groundwater also, because we are using lot of fertilizers or pesticides or soil amending agent. Those by leaching or by rainwater can go to the river water, so water is polluted. Sometimes industrial waste also, without careful observation, we put into the river water or nearby the source of the river water, so the river water become contaminated. So this is a river water is our fresh source of water, right? So we are contaminating this way. Another one is climate change. Glaciers and ice packs are melting in some areas, affecting freshwater supplies. Moreover, because of global warming, there are more and more flood, drought, and heat waves. Climate change is therefore worsening the water crisis. Some places we will see water is no water is there. There was earlier there was water, but now the water is dried out, especially in regions that are already under water stress. That means dry areas. Some dry areas due to climate change, due to global warming, there is more water is reducing. So the amount of fresh water day by day is reducing. This is number two for water scarcity. Number three is growing freshwater demand, which is quite obvious, because over the last 50 years, world population has doubled and it is continuous to grow. As a result, the use of water to drink, cook, and meet other needs have been tripled. One of the statistics shows it is triple. As the global population is expected to boom in the coming decade, water resources need to be managed more efficiently. So whatever water we have to purify it, and better to recycle and reuse the water. That means regeneration is needed. I am stressing this term, recycle, reuse, and regeneration. These three are these terms. Later on, I will explain why. There is a reason why I am stressing in these three terms: recycle, reuse, and regeneration. Overuse of water. Of course, this is a problem. The misuse of water resource is another big issue leading to water scarcity. Inadequate management of water resources, whether it is for agricultural use or other domestic use, because sometimes we see in our village area, people are opening the tap and then not closing it. It is very common scenario. I have seen it in lot of places. So the water is flowing, 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 and it is reducing, right? Fresh water is reducing, or we are wasting our water. Now first come, what are the types of pollutant in water? As I mentioned earlier, there can be inorganic pollutant, organic pollutant, microbial pollutant. Inorganic pollutant, first come metal and metalloids, or some inorganic radicals, let's say phosphate, sulfate, those. So inorganic pollutant, first it comes to our mind is heavy metal pollution. Heavy metal pollution by metals, the metals which has high relative atomic mass, those are known as heavy metals, such as lead, mercury, arsenic. Those are known as heavy metal, and those, if present, then the required limit, then we call it is heavy metal pollution is going on. Unfortunately, Malaysia has this heavy metal pollution both in air and water also. Some of the paper is there which is writing in this issue again and again. I will show just a small 2 3 issue. So this is heavy metal pollution. Now heavy metals are necessary for our body also. We cannot, it is not like that we stop using all the heavy metals so there will be no contamination. We cannot do that. These are macronutrient also. Let's say cobalt, copper, zinc, iron, these are macronutrient for our body. All living animals or plants need that. Micronutrient is copper, nickel, chromium, iron. Highly toxic is cadmium, lead, silver, mercury, those. Precious element comes platinum, silver, and gold. Platinum, silver, and gold. Silver is also toxic to some extent. Gold is less toxic but still toxic. And actually, in case of Malaysia, if we tell about Malaysia, then we are suffering more for lead, copper, manganese, cobalt, zinc, iron, chromium, those. There is a reason, because copper mining is going on in Malaysia, already done already in mine city market, right? So nearby all the field, if we check all the paper, it has been reported, nearby all the field, there is lot of copper found in the soil. So this is copper pollution. This will be slowly leached out into the water, and then the water will be polluted by over excess of copper, right? So metal toxicity. Metal toxicity is determined by metal's inherent ability to negatively impact the biological activity. Usually metals are all carcinogenic or mutagenic agent, and it can destroy the nervous system. It can cause deformity in the body also. If pregnant mother is taking heavy metal containing water, then the baby can have deformed body also. Even sometimes some of the metals are responsible. It is told that mixture of metals are responsible for autism also. Nowadays autism is a great issue. Autism or some Down's syndrome also can be there. Although the real cause of autism is still unknown, but heavy metal is one of the cause, it is told by some of the researchers. So some cases, even it is extreme amount, it can cause death also. And arsenic, we all know that arsenic can cause cancer. That's the thing. Even lead also. So what is the fate of metal in aquatic environment? It is very persistent. It doesn't want to go. So what it does, it actually goes to the food chain. It first goes to the plant, aquatic plant. Then from aquatic plant it goes to the small fish, then to the large fish, and from the large fish we are the final member of the food chain. So it comes to us. So this way it is bioaccumulating. It is bioaccumulating. And sometimes it precipitate in hard water also. In hard water where there is hydroxide containing metal, let's say calcium hydroxide and those, so magnesium hydroxide, it precipitates, iron oxide precipitates, copper oxide precipitates, and there it is present. And it is not, it is persistent in nature. It doesn't want to dissolve so easily or so quickly. And in acidic water, it is very easily dissolved. Okay. And high temperature also it is dissolved very easily. So let's say if we consider the case of Malaysia, this is hot country, so there will be naturally lot of heavy metal pollution. A lot of papers are reporting these things. Here we have used some metal cadmium toxicity, which is common: hypertension, vomiting, coughing, diarrhea, deformity in bones, and abdominal pains. Copper also similar types of toxic effects. Now, sources of heavy metals. What are the sources? Mining. As I mentioned earlier, mining is the first source. Waste disposal, corrosion industries. Corrosion industries, we are using metal plating, right? Sacrificial metal plating. Then it comes industrial smoke. Of course, industrial smoke can then metal plating industry also can give. Agricultural pesticide also have some metals, so it comes out into the environment. Some fertilizer also have heavy metals, and those comes, and then slowly it bioaccumulate in the soil, and then it runs to the water. So this way heavy metal pollution is going on. Here heavy metal, this is a report from the from Pahang area. It is Jebing industrial area. This is a paper cutting which we got from 2022. This is telling that anthropogenic input from mining and national and industrial activities such as wastewater discharge from electroplating, smelting, corrosion of copper, tubing, metal engraving industries is significant source for this area heavy metal pollution. Large amount of untreated industrial sewage is also there, and then water bodies are contaminated also. This is a paper cutting, so we can see that countries especially Malaysia is also having heavy metal pollution up to a larger extent, not in water only, air also and soil also. It is a very critical issue. Eh, Here another statistics. Water pollution in Malaysia is caused by both point and non-point sources. This is very important to know. Sewage treatment plants, manufacturing and agro-based industries, animal farms have all been identified as point sources because they are directly throwing heavy metal containing water. Non-point sources are mostly diffuse, like agricultural activities, surface runoff, as I mentioned earlier, leaching by rainwater. According to Malaysian Environmental Quality Report, Department of Environmental identified 17,991 water pollution point source in 2004. This statistic slightly changed now, but the number is alarming. It is not that the number has been reduced. The number is not reduced. With the majority of them being sewage treatment plant, manufacturing industries, just the change is sewage treatment plant was 54%. Now it is reduced around 34%, 35%. But manufacturing industries became more for Malaysia. Animal farms, agro-based industries. Here is the figure one on the right side. We can see that how all the all the features are polluting our fresh water in Malaysia. There is another pollution alarming in Malaysia, that is dye pollution. Why? Because Malaysia has a very popular industry, that is batik industry. So batik industry is producing lot of dye polluted water. Dye is a substance used to color textile, paper, leather and other materials in such a way that coloring is not easily altered by washing, heat, light or other factors. See, from this line we can understand that dyes are very persistent in nature. These are usually aromatic ring containing compound which is very difficult to be broken up. Synthetic origin, these dyes are synthetic origin, complex aromatic structure, stable in environment, as I mentioned earlier. It has some metabolites which are toxic and threat to environment and organisms. So there are actually several types of dye. I am not going in details because we have other organic pollutant also. There are pharmaceutical products, hormones, even some hormones, pharmaceuticals product, herbicide, pesticides, those are also come under organic pollutant. So how dye is polluting our environment? The most serious environmental concern with dye is their ability to absorb and reflect sunlight. Light absorption reduce algae photosynthesis. This is the main source of pollution. When algae cannot go for photosynthesis process, they will die, and there will be lot of organic biomass in the river water or lake water. So it will be a kind of pollution, right? It will have a serious impact on food chain. Many dyes and their byproducts are carcinogenic, mutagenic, and toxic to the living things. Dye workers have been reported to have triple primary cancer. Three places the cancer can happen: kidney, urinary bladder, and liver. Textile dyes can cause allergies like contact dermatitis, respiratory disease such as well as allergic reaction in the eye, skin irritation and irritation of mucous membrane and the upper respiratory tract, the membrane of the respiratory tract, outer membrane of the respiratory tract. Azo have toxic effect, especially they are carcinogenic and mutagenic. The highly toxic and mutagenic dye reduce light penetration for photosynthesis, resulting lack of oxygen and limiting downstream beneficial uses such as recreation, drinking water and irrigation. What will happen? BOD, COD will be changed. Dye containing water, we will see that there will be BOD, COD will be changed. The presence of very small amount of dye in water that are still highly visible has serious impact on quality and transparency of water. This one we always see. Covalent bonds are formed between reactive dyes and cellulose, woolen, and polyacrylic fiber. Certain reactive dyes have caused respiratory sensitization in workers who have been exposed for this job. Here comes the batik industry. Unwanted substances in batik wastewater are harmful for human and aquatic life. The presence of dyes, other chemicals, and heavy metals in batik wastewater, such as resin, wax, and silicate. These three always present with batik wastewater. So what happened? There are multiple components coming from batik wastewater. Not only color, there are wax, silicate, and resin also. To some extent, sometimes some heavy metals are also present due to processing of the dye. So, and there are of course some phenolic compound also. So now it became multi-pollutant system. I repeat the term, not single pollutant system, multi-pollutant system. Here comes the challenge. Because we can go for the process, one process is efficient for phenolic, but maybe this process is not efficient for suspended solid, maybe not efficient to correct the BOD or COD. Those things needs to be considered. That's why I again and again mention multiple treatment method is needed for wastewater treatment. uh, in the wax contain high level of organic pollutant found in batik. If we go to the next slide, here also, batik wastewater always we will see the alkaline pH is there. It has intense color. BOD, COD is not balanced there. And there are large volume of different types of pollutant. In my next table, I will show that how uh, batik industry COD level in batik industry wastewater can range for 34 milligram per liter to 20,900 milligram per liter. Heavy metals such as chromium, lead, calcium, silicon, magnesium, copper, ferrum, and zinc also have been found in batik wastewater in some studies. Let us see the statistics, and it is 2022 statistics. This is very important. Let's see this table. We can see that effluent from batik industry, pH, BOD, COD, suspended solid, total suspended solid, heavy metal concentration and others, how it is too high amount. It's too high amount. BOD, COD, if we consider COD, it's too high. Number 6, COD is 13.2, 1320 and BOD is 81.74. These are all real statistics. From 2022 paper we have collected, and we can see that the water is highly toxic and the pH is also not normal. pH is usually alkaline in case of dye industry wastewater. Now, how we can treat this wastewater? We can treat this wastewater by amorphous phase carbon or activated carbon. There are some nanocarbon also. Carbon has amazing chemistry. Carbon, based on its uh, orientation, can be nano or microstructure also. But there is a strong debate going on now that for water treatment, for industrial scale or large volume of water treatment, whether nanoscale carbon usage will be economical, will be toxicity free, or we are introducing secondary pollutant to the nature. In that case, there is a debate for amorphous phase activated carbon with amorphous phase activated carbon or biochar with nanocarbons such as CNTs or graphene and graphene oxide. Of course, both of them has some pro and cons. Both of them have some positive side and negative side. Later on we will discuss in our different slides. So activated carbons are graphite like layers. Activated carbon comprises of graphite like layers. It has lot of pores, micropore, mesopore and macropores. So micropores is the smaller size pore below 2 degree angstrom, and 2 to 50 is mesopore, and over 50 angstrom is macropores, which act as tunnel, which doesn't take part in the adsorption process. Adsorption is a process for removing the contaminant, right? There are a lot of other process also, as I mentioned, but my topic today is based on adsorption. Other process just I will touch a bit. So why we are in favor of activated carbon? Initially, I am trying to say the positive side of amorphous phase activated carbon. Later on, I will discuss that what is the beneficial effect of nanocarbon also, and what is the disadvantage of nanocarbon, for which industrial scale usage sometimes becomes difficult. So activated carbon has more surface area. We can easily prepare it if we use renewable sources like biomass. We can tune its surface property. That means we can change the preparation method, and different types of surface functional groups can be attached. Regeneration. As I mentioned earlier in my slides, that I will emphasize on 3R: reuse, recycle, and regeneration. Regeneration means that the same activated carbon we are using, we can use it for several times after purification. So it is an economical process, but nanocarbon regeneration is to some extent difficult because it is very small particles, so it will be quickly dispersed into the water, which we don't want, because nanocarbon itself can be contaminant for the water. Therefore, we have to strictly prohibit nanocarbon leaching into the water environment, aquatic environment. After the treatment, we have to carefully remove it. But sometimes how much careful we are, we cannot control the things. Eh? Later on, I am showing in my slide that why it is so much contaminating. Especially CNTs. CNTs are contaminating factor for water. But CNTs also have very good things, very good properties. It can be used as fertilizer also. So therefore, as I mentioned earlier, each and everything has its positive side and negative side also. Even CNTs, graphene oxide, graphene, those are important for seed germination, but in very minor quantity. In very minor quantity. Used activated carbon, we can just thermally activate and can use as a biofertilizer for the plant. Especially orchid, if we see orchid are always grown on activated carbon, right? Cool. So this is our carbon family, right? It's a big family. It can be graphene, single wall carbon nanotube, micro wall carbon nanotube, fullerene, which is very costly. It can be like that. Graphene is less costly because we can extract it from graphite by Humar's method, but the method is uh, acid treatment method, and this method is not user friendly. I will tell it is not user friendly green method because there are a lot of acid involved, but nowadays there are some process of green synthesis of graphene oxide from graphene. The surface functional group is less, but still those are working also. That is the thing. Fullerene is very costly, and single wall and multi wall carbon nanotube we have to prepare by some method. Those methods are slightly costly method. These are all nanoforms of carbon. These are all nanoforms of carbon, and activated carbon is the amorphous phase of carbon. Activated carbon or amorphous phase carbon, before activation, can be divided into biochar and hydrochar also, or both of them has great use for water treatment. So this is very important issue, that activated carbon can be considered as mother nature purifier. It is always called mother nature purifier. Even it is called that preparation of activated carbon is not a science. We should not tell it as a science. It is an art to prepare activated carbon, because based on biomass type and preparation condition, based on the starting substance, based on the reactor type, based on the pyrolysis type, we can shape activated carbon in different way. We can design it. Even the functional group also we can tune. It is a mother nature purifier. Basically, activated carbon is known as mother nature purifier. And preparation of activated carbon is not considered as a science. Several book has written it as an art. Preparation of activated carbon is an art, they told it. So here we can see that why activated carbon is so important, because it is resistant to highly acidic and basic media. It has large surface area. It can go for physical bonding process also for with pollutant, van der Waals force or hydrogen bonding, by which it can catch the pollutant. It can absorb gaseous pollutant also, liquid pollutant also. It can absorb bulkier pollutant like iodine vapor also. And cost of carbon, if we can control, then it will be great, because in the market we are getting activated carbon which is from non-renewable sources, that is from fossil fuel. But if we can mimic the environment under the earth, if we can mimic the environment up to a certain scale and use some biomass substrate, thrown away biomass substrate, which is of less cost, then we can convert it to activated carbon. But we have to remember, activated carbon is very specific in nature, just like catalyst. It is not like that one type of activated carbon I have prepared from a mango leaf, that means this activated carbon will be useful for all types of pollutant. It is not like that. They are very specific in nature. Maybe only one type of pollutant will be caught by that specific type of carbon derived from mango leaf. These things we have to, that's why trial and error method, that's why the term art came, that preparation of activated carbon based on its purpose, based on its application, is not a science, it's an art. It is told by several authors. Eh, we have to go by trial and error method to check that whether the activated carbon will be taking our targeted pollutant or not. Or will take first, it is okay, it is taking the pollutant first, but later on, after certain time, it is dissolving the pollutant also. Because we know that adsorption and desorption of pollutant is consecutive phenomenon. It goes on together in the system, which makes our pollutant removal difficult also. That's why getting equilibrium point in adsorption process is difficult. Later on, we will see how many types of adsorption is there. In my title, there is batch adsorption plus column adsorption also, right? So there we can understand that major adsorption is batch and column adsorption type, right? We have three types of activated carbon: powdered, granular, and activated carbon fiber. Now the question is where which is used. Batch adsorption process. In batch adsorption process, in the batch reactor, we put the activated carbon and we constantly stir it with the polluting water. So powdered activated carbon is better here. Granular activated carbon is good for column-based adsorption process, where in the column the carbon will be static, the carbon will not move. Remember that column-based adsorption process, the water will flow continuously. That's why it is known continuous flow column-based process, but the carbon will be stagnant and the carbon needs to be granular. We cannot use powdered activated carbon in column due to axial dispersion and cannot treat the wastewater. Column-based adsorption process always in the industrial system we use, and batch adsorption process also, batch reactor also we also use before the column adsorption process at the last stage. Activated carbon fiber is used for electrode material, sometimes purification process also, sometimes fertilizer also, sometimes adsorption process also, or sometimes membrane fabrication also. But during membrane fabrication, we have to remember that activated carbon fiber is an inorganic phase, right? So in the maximum membrane is polyvinyl acetate, cellulose acetate, those are organic phase, right? So when we are mixing the organic phase with the inorganic phase, the things needs to be homogeneously dispersed. If it is not homogeneously dispersed, what will happen? There will be agglomeration tendency and water channel will be blocked. So membrane separation process or membrane purification process will be failed. So these are some challenge for membrane separation or purification process. Activated carbon until now has been used for water treatment, gas treatment, pharmaceutical manufacturing, food and beverages, air and gas treatment also. As I mentioned earlier, activated carbon, we can get biochar based on the temperature. In presence of nitrogen, if the temperature is within 400 degrees centigrade, the pyrolysis process will give us biochar from biomass. If the process is carried out in underwater at high pressure, only in 250 degrees centigrade or 200 degrees centigrade, we will get hydrochar. Since water is present, the term came hydro. So hydro and bio, what is the difference? Biochar is dry torrefaction, dry process. There is no water present, and hydrochar, there is water present. The reason for giving water is at high temperature, at 250 degrees centigrade or 200 degrees centigrade under pressure, there is lot of pressure. Under pressure, water can work as both acid and base. It will form OH ion also, H plus ion also. That's why it can easily disintegrate the biomass substrate and can produce uh, hydrochar, which has lot of functional group present. Later on, hydrochar or biochar both can be activated to give activated carbon, which will have more surface area. Why we activate biochar and hydrochar? To have more surface area. We can use a small amount and we can remove lot of pollutant. That's why we use like this way, right? This is some common types of biomass. In here, we have used two steps, right? First, we have converted it to biochar around 400 degrees centigrade. When we activate the carbon, the surface became porous like this. We can see right side, in my right side FESM picture, we can see that it is porous. So these pores are going to collect the heavy metals or the dye pollutant, just like a sponge. We can remember, just like a sponge we use in our home for cleaning, activated carbon surface is just like a sponge. Okay. Here some common example for Rotten base sawdust. If we see the plate A is showing raw rotten sawdust. After 200 degrees centigrade, the rotten sawdust became flaky like this. After 260, it has some pore. After 230, it has smaller amount of pore. So we can see that by increasing the temperature from 230 to 260, from D to C plate, there are more bigger size pores, right? So that means in hydrothermal carbonization, if we increase slightly the temperature, the pore size can be increased. But there is less amount of pore, right? Not lot of amount of pore. In second step, what we have done, from rotten sawdust, from rotten sawdust, we have extracted the cellulose by hydrolysis process. Those cellulose we did the hydrothermal carbonization at 200, 230 and 260. So we got a new types of carbon, which is globular shape, cluster shape, carbon globules. These types of carbon are not that much good for adsorption, but for electrode material, it has been found good. It has been found to work better. Eh? So these are some use of activated carbon. Okay, why CNTs may be suitable to be used as catalyst support? Sometimes we go for water treatment catalytic wet air oxidation, where CNT is used as a catalyst and over it is some metal is doped. Let's say copper metal is doped or vanadium metal is doped, gold metal is doped, and then we pass oxygen in the water, which is called catalytic wet air oxidation. In this phase, the pollutant will be oxidized and there will be some simple fraction of molecule which will be adsorbed by CNT or it will be disintegrated. So water will be purified. Obviously, CNT is a good support because of its hardness, strength, electronic properties and adsorptive properties. Thermal properties also, it can withstand high temperature. Coming to the activated carbon. Like activated carbon, what are the adsorbent available in the market? Silica gel, activated alumina, polymer and resin, clay and zeolite. So among them, why we are choosing activated carbon for, we can make adsorbent with all of them and people are using it also in industry. But I am talking here only for activated carbon. There is a reason I will show afterwards. We have some research work also we can show here, that same activated carbon we can use for adsorbent material, we can use for membrane material, we can use for batch adsorption, we can use for column adsorption also. Okay. Now, what is the toxicological effect of CNT for which we were nervous, bit nervous for using CNTs and graphene? There are some toxicological effects. So, during using it for water treatment, we have to make sure that it must not leach out openly into the water. The process stream needs to be clean because it has ecotoxicological hazard. CNT has tendency to destroy the epithelial cell of lungs. If CNT's growth process cannot be optimized and controlled and cannot be ensured, the leaching of CNTs from the membrane surface, it can cause health hazard also. Furthermore, CNTs are very costly to produce and it is difficult to work with. And the people who are handling CNTs for long time may have the tendency for lungs cancer. It is expensive to prepare also. But activated carbon, so far, these sorts of problems are not found in activated carbon. So these are basically different temperature range by which we can thermochemical conversion process. We will tell thermochemical because we can change the temperature. That's why the word thermo. And we can add some chemical also to get our desired carbon material. Again, I am mentioning carbon preparation is not a science. It is rather considered as an art. Which pollutant we are targeting. That's why we have to prepare again and again and target our exact pollutant type and exact environment of the pollutant water. If the pollutant water has a multi-component, maybe a very good quality carbon can fail. It can fail. It happened in my lab also. Then we have to change our carbon type. And we have to take the help from zeolite, limestone, and we have to use the consecutive column. Here comes the column. We have to use the consecutive column to purify it, not only granular activated carbon, right? So again, I have mentioned earlier also, multiple system is needed to treat industrial wastewater or any types of wastewater. This is biochar. Biochar can be used as fertilizer. Biochar preparation method we can tell as dry torrefaction method because biochar is prepared under nitrogenous atmosphere. No water is added. Below 400 degrees centigrade temperature it is formed. So this is the positive side of biochar preparation. Biochar will take some pollutant material but not up to a greater scale because biochar, since we have used less temperature, so less reaction time is available there. So there will be less porosity. That's why biochar sometimes used for fertilizer and it is kept for activation to prepare activated carbon. Hydrothermal carbonization, as I mentioned earlier, hydrochar will be produced. Hydrochar also can be a good material for electrode and hydrochar can be a good material for heavy metal adsorption. But some cases, if we need more surface area, we have to activate it. But hydrothermal carbonization positive side is lower temperature. Within 250 degrees centigrade, we can get the hydrochar. So why we use biomass waste? Because here we are solving threefold problem. Waste minimization. There are a lot of biomass waste. Suppose peel of fruits, suppose wood sawdust, the things which we are throwing off in the environment. So that is waste management, right? We can take it and convert it to useful material. That is reuse, right? Earlier I used the term reuse. We can reuse this waste material, recycle this waste material as valuable component. Reuse and recycle. So two R is here. Regenerated. The valuable material which I produce is activated carbon. Those can be regenerated to remove the pollutant material. So there is a strong nexus between, a very strong nexus between waste management, carbon preparation, environmental purification together. Even soil amendment also, right? So the same thing can go for different purposes. That's why there is a strong nexus between different fields, right? This is hydrochar, biochar and activated carbon. What is the positive side and temperature condition, preparation condition? This is the summary. As I discussed earlier, this is the summary only, nothing else. So adsorption process, there are membrane process, physical process, biological process, ion exchange, precipitation, sludge formation and adsorption process. Adsorption process is easy and cost effective. We can use CNTs also, CNTs and graphene also. In graphene and CNTs, just the bonding of carbon is different. CNTs can be micro-walled or single-walled or micro-walled carbon nanotube. So CNT preparation, there is arc discharge, laser method and chemical vapor deposition method. Our lab has chemical vapor deposition method in engineering. The process is bit costly and complicated also. We have to be very careful, otherwise there is a burnt off of sample and we can produce very less amount. It is a very big apparatus, it has very big capacity, but to make the property nice and the surface free from toxic element, we have to treat very small amount to convert it to CNTs. This is the practical problem in preparation of CNTs in larger scale. Furthermore, in CNTs, some metallic pollutant can be present because we use metal as catalyst to produce CNTs in CVD method. This is some method we can get it. So here, critical factor for using CNTs in water treatment. This point we should be noted. CNTs are required in high volume for absorbing water pollutant and it is needed in high concentration. On the other hand, pristine CNTs are themselves are problematic because of their generic impurities such as metals and carbonaceous agents that cause nanosafety issues. Very important case. There are metals because we use metal catalysts, let's say iron or cobalt catalyst. Later on, I will show one of my student has converted activated carbon to CNTs and he has used these two catalysts. So these two catalysts after CVDT method, we cannot remove from CNT surface, right? So we are introducing those metal as pollutant also into the environment, right? The absorption of various organic pollutants such as humic acid, tannic acid alter CNT's properties and increase its stability. So CNT doesn't want to degrade. Moreover, biological adsorbents such as some microbe has potential to change the CNT surface. Some bacterial intercellular enzyme catalyze the formation of hydroxyl radical or hydrogen peroxide through redox reaction that produce carboxylated CNTs. This convert hydrophobic pristine CNTs to hydrophilic CNTs. What will be the problem? Hydrophobic one, it will want to be separate from the water, but hydrophilic one, it will be easily dispersed into the water. Then we are in trouble, right? So this can be happen for some simple enzymatic reaction in nature. That's why it is difficult to use CNTs. So before using CNT as nanocomposite or as photocatalyst for wet air oxidation or photocatalytic treatment of water, we have to follow its, we have to know about its reactivity, toxicity and fate to the environment. Because CNT after using, if we cut it or grind it, there will be some aerosol of free CNTs. Those are also harmful. So this we have to be careful. So raising the issue for water treatment, usage of nanosorbent, nanomembrane, should we use nanosorbent or nanomembrane? Is it feasible or not? There is a great debate. As I mentioned earlier, both of them have positive and negative side. If we can ensure metal-free fabrication of CNTs by CVD method, then can use. If we can ensure that our CNTs should be hydrophobic, will not become hydrophilic, then okay. If we can control the growth mechanism and we can make it leaching free, then also we can use it in membrane synthesis process. Adsorption process, we need to understand what is adsorption, principle of adsorption process, adsorbent and adsorbent. These are very simple things, and what are the factors affecting the adsorption process, we will go very quickly. If we see here, let us see that this video, just let us see what is adsorption and adsorption.
And adsorption. Some tea accidentally falls while you're studying. What is the best way to remove it all immediately? Click on the right option. Yes. Now watch the tissue paper suck away the spilled liquid quickly. If we had used ordinary paper, the tea would not be completely absorbed. Tissue paper absorbs a liquid, and ordinary paper adsorbs a liquid. How are these two different? Let us learn more on them. Let's understand absorption and adsorption a little better. Absorption is the passage of one substance into or through the bulk of another medium. The absorbed substance spreads to saturate the whole of the medium to form a solution. The mixing with the other medium's environment is so well that one fails to recognize its existence as a separate entity. In contrast, what happens during adsorption? Adsorption is the addition or sticking together of molecules of a gas, liquid, or dissolved solids to the surface of a solid or sometimes a liquid. The molecules are loosely held by the surface and can easily drop off. Let's see the difference between these processes. Absorption is seen in common day examples. Perfume spray is absorbed by our skin. Crisp finger chips turn soggy because they have absorbed moisture from the air. One substance is well soaked into a different medium. What about adsorption? Here is a jar containing a red dye dissolved in water. Look, what happens when a solid pellet of carbon is dropped into the jar? Well, isn't that surprising? The red color has almost disappeared in the jar. Why? The charcoal pellet has minute pores on its surface that cause the colored particles stick to it. The red dye undergoes the process of adsorption. Shake or warm this jar, and lo, you get back the red color. Adsorption can be easily reversed by simple heating and is transitory. When a substance is absorbed in a different medium, it's called absorption. Usually, absorption cannot be reversed by simple means, although it may also be temporary. Now let's focus on adsorption by carbon and some practical applications. We could use adsorption for such diverse things like in deodorizing air in a refrigerator, decolorizing sugar solution, and controlling excessive acidity. Activated charcoal in a gas mask attracts toxic gas molecules, allowing the person wearing the mask to breathe fresh air. Drag the carbon pellet to each of the units displayed here, one by one, and observe the reactions that take place. Identify whether a solid or liquid or gas is adsorbed by carbon in all these cases.
Okay, thank you for observing it. It's a very interesting I should go. Okay. So adsorption is the removal of dissolved substance from solution using adsorbent material, which can be activated carbon, activated clay, silica gel, alumina, anything else can be there, right? Adsorption is a process that occurs when a gas or liquid solute accumulate on the surface of the solid or a liquid adsorbent, forming a molecular or atomic film. First, a film will be formed, and then inside the activated carbon pores, the pollutant material will enter. This is called adsorption, but it will not go completely inside. Then it is absorption. Just now in the video, we have seen that what is the difference between adsorption and absorption. Adsorption is a separation process. Adsorption is a strictly surface phenomenon. Remember that adsorption is a surface phenomenon, but absorption is overall full phenomenon. And adsorption and desorption takes place simultaneously. That's why during pollutant removal, the equilibrium time and equilibrium of the system getting sometimes become difficult, because pollutant is going, let's say the red dye is going, and after 5 hours it is coming back again from the carbon. That's why as soon as the carbon has adsorbed the pollutant material, we have to separate it. Okay. So adsorbent means adsorbent can be carbon, clay, as I mentioned earlier. This is the process of adsorption process. Adsorbent is our carbon, adsorbate is our pollutant, adsorbate, ATE is our pollutant, and adsorbent is our carbon or any types of material what we are using for pollution removal. Okay. The degree of adsorption depend on temperature, pressure, and surface area. Obviously, if the surface area is more, there will be more adsorption. To some extent, by temperature increasing, adsorption process will increase due to kinetics force. But sometimes opposite phenomenon also can take place. Until certain pressure, the adsorption process will be okay. After that, it will be no effect. After certain pressure, if we increase also pressure, the adsorption process will be same. That is the rule. So this is the mechanism of adsorption. We can see the first the pollutant molecule comes into the surface and then slowly enter into the pore. The right side is showing the photograph of adsorption process.
Mechanism of adsorption. Adsorption arises due to the fact that the surface particles of the adsorbent are not in the same environment as the particles inside the bulb. Inside the adsorbent, all the forces acting between the particles are mutually balanced, but on the surface, the particles are not surrounded by atoms or molecules of their kind on all sides, and hence they possess unbalanced or residual attractive forces. These forces of the adsorbent are responsible for attracting the adsorbate particles on its surface. The extent of adsorption increases with the increase of surface area per unit mass of the adsorbent at a given temperature and pressure. Another important factor featuring adsorption is the heat of adsorption during adsorption. There is always a decrease in residual forces of the surface. That is, there is decrease in surface energy which appears as heat adsorption, therefore is invariably an exothermic process, and enthalpy change delta H of adsorption is always negative. When a gas is adsorbed, the freedom of movement of its molecules become restricted. This amounts to decrease in the entropy of the gas after adsorption, that is, delta S is negative. Adsorption is thus accompanied by decrease in enthalpy as well as decrease in entropy of the system. Adsorption is spontaneous process at constant temperature and pressure. Gibbs free energy, that is delta G, decreases. Delta G is equal to delta H minus d delta S.
So this is the basic differences between adsorption and absorption process. Some absorption process is endothermic, adsorption is exothermic process, decrease in temperature, right? So this is the physical adsorption when there is no chemical bond formation over the surface, but if there is chemical bond formation, that is with the surface functional group, then we call it chemical adsorption. We can understand chemical or physical adsorption by kinetics studies and isotherm studies, okay? Later on in my slide I am showing here. So this is physisorption and chemisorption. This is two types of adsorption process. Both can take place in batch adsorption or column adsorption process. So adsorption isotherm, there are basic types of adsorption isotherm. In adsorption isotherm, we actually see under constant pressure, the residual pollutant remaining in water and the pollutant adsorbed over the adsorbent surface. The relationship between these two is known as adsorption isotherm. Based on different adsorption mechanism, the isotherm has been given as a 2-parameter model, as a 3-parameter model, 4 or 5-parameter model. Those are basic theory. We can see such as Langmuir model, which has a 2-parameter, Freundlich model. This is type 2 isotherm. We can read it from the theory. Type 3 adsorption isotherm. It is slightly deviation from Langmuir model. Langmuir model is typical. Langmuir model is L shape. Okay. And type 4 is multiple phase transition. That's why the graph is like that. Okay. Initially L phase and then again trying to become S, right? So that is with pressure, it is trying to become S. This is type 4 isotherm. Okay? Type 5 isotherm is like that. This one initially no adsorption, but after certain time there is some adsorption going on. Okay, this is type 5 isotherm. Equilibrium relationship of adsorbent. Equilibrium point is the point where no pollutant will be taken by the adsorbent material. That means the system is exhausted, the carbon is exhausted. This is known as equilibrium point. So common types of adsorption isotherm, if we go for Freundlich, this is favorable shape. We can see the different shape. Linear shape, Langmuir shape is L shape. Freundlich is slightly, not L shape, it is slightly parabola shape, but not L shape. Okay, so it is favorable. Langmuir, what is the favorable shape of isotherm? It is given here. So these are 1 parameter, 2 parameter models. This we have to see in the theory classes. 5 parameter model, Fritz model. This is our experiment. We can see here we have removed the copper. We have used 6 concentration, 50, 60, 70, 80, 90 and 100. And then we have removed the copper by using mangosteen fruit shell, which was granular activated carbon. Okay, so this is our batch adsorption taking place. So with time, this way the pollutant was removed. We can see approximately 300 minutes, after 300 minutes the system reached the equilibrium. Actually after 150 the system is not taking significant amount of pollutant, right? Similar types of result or repeating results were coming. So this is the equilibrium point. Okay, so after 150 it reached to the equilibrium point. This is phase 1 for adsorption process, and after adsorption some absorption also takes place. Obviously there is some absorption also takes place inside the water. This one we will understand by studying intraparticle diffusion model, Boyd plot or film diffusion plot. So this is the basic adsorption process. Early stage, slowly some molecule enter, then later on the full hole is filled up by the molecules, pollutant molecules, and in equilibrium system, whatever be present there, the pollutant is there, they are not coming out of the hole. All of them entered into the hole and they are not coming out. So the system is in balanced condition. So this is equilibrium condition. So what we have done, we have prepared some hydrochar from cellulosic waste, and then this hydrochar was activated by potassium hydroxide. We have used design of expert. We have performed 29 experimental run to check how much copper is removing by each run and how much active carbon is there. I mean yield, what is the yield of the carbon. This is our basic apparatus, pyrolysis apparatus, by which we have prepared our activated carbon. This is a hydrothermal setup. We have used RSM technique, box Benhanken design. I am not going elaborately to it because time is constrained here. We have to finish quickly. We have used BBD design where we have 3 variable: temperature, activation time, and ratio of hydrochar with KOH. So these were our basic thing. We have changed our time from 1 to 3 hours. Our ratio to KOH and hydrochar 0.5 to 2, and carbon dioxide gas flow rate is 50 to 100. So there are 4 variables also. So in this 4 variable, our software suggested 29 experimental run. So we have done 29 experiment and we have seen what is the removal percentage of copper and what is the yield percentage. We have tabulated it, and then in software we have the optimization menu to check where we can get, how we can prepare the activated carbon where we will get maximum yield with maximum removal percentage, because we need maximum yield also. If our yield is less, what will happen? The process will not be economical. We don't want that. And now there is opposite condition. When there is removal percentage more at higher temperature, yield is less there. When gas flow is more, then okay, good quality carbon is producing, but yield is decreasing. So the interest region is different, right? So when removal percentage is optimum, yield is not optimum there. So it is a confusing situation. That's why the software has optimization menu. We will click that and ask the software for the optimized point to prepare the carbon. So we have done that, and then ANOVA analysis has been carried out. We have seen which factor has more effect. We can see here from the data, from the sum of the square value, that temperature has more impact on carbon preparation, right? It is 55.21, okay? So this is our optimum process optimization ramp. We can see the software has suggested from Rotten sawdust, we can use 752 temperature, time 1 hour, 86 minutes, ratio 2, and then gas flow is 51.23, carbon dioxide gas flow obviously. Then we will get the removal percentage. Predicted was 90.55. I mean, software told that approximately I can get the removal percentage 90.55, but I get 91.45. Predicted yield was 43.02, but experimentally I got 44. So my error percentage is 0.99 and 3.78. So okay, I am in the range. Okay, not my experimental data didn't deviate from the practical data too much, right? from the software prediction too much. So software prediction and my experimental data is nearby, not too much erroneous result by experiment. So this is some parameters for standard deviation in our data and correlation R square value and those. These are some basic equation for percentage removal of copper and yield percentage. This is for pollutant mitigation. We can see two variable with time and temperature, how the removal percentage is varying. This is 3D response surface plot. We call it 3D response surface plot. Here we can see the shape is umbrella shape. It seems that somewhere else in the middle, when the umbrella is showing some bulkier portion, there the maximum removal percentage can be seen, right? Similarly, when we go for yield, we can see there is no umbrella shape. This is completely straight cut reaction. When the temperature is increasing, yield is decreasing. When the ratio is increasing, yield is decreasing. When the time is increasing, yield is decreasing. Obviously, there will be more reaction, more volatile material will comes out, more ash will form, more sample will be burnt off, so there will be less carbon product, right? So this is our surface characterization. We can see the hydrochar has surface area only 7.02. After activation, it became 825.50. And as I mentioned earlier, the second graph is showing L pattern, L and S pattern, mixed up of L and S pattern um, isotherm for nitrogen gas adsorption in BET isotherm, which means that our sample has some proportion of micropore with some mesopore inside it. Okay, for liquid phase adsorption we need mesopore, but since we are dealing with heavy metal needs smaller size of pore, so it is okay, we have lot of micropore also. For gaseous adsorption we need more micropores. This is FTIR data. This is our XRD data. Raw rotten dust have cellulose and amorphous cellulose and crystalline cellulose. So two peaks were there. Hydrochar, we can see that amorphous portion is deleting slowly, and raw rotten dust based carbon completely amorphous type carbon, right? No sharp peak was seen. Here ultimate analysis shows that percentage carbon was increased from raw rotten dust to carbon, activated carbon, from 39.81 to 87.04, which is quite obvious, right? That means we have got pure carbon by activating the sample, so we need it for pollutant removal, right? This is our TGA analysis. This is our surface. We can see after hydrothermal carbonization, there was globular carbon form, but after activation, there was lot of pores available over the surface, which can catch the copper pollutant from water. This is Langmuir isotherm. We have used this equation. This is Freundlich isotherm. We have used this equation and Temkin equation also, and we run this experiment in 3 temperature, 30, 50, and 70. We can see that as much as the temperature was increasing, Langmuir monolayer maximum capacity, that is Qmax, was increasing from 20.83 to 21.74 to 22.21. Similarly, Kf was also increasing in Freundlich isotherm, which is affinity factor. That means as the temperature was increasing, more pollutant are prone to enter into the pores of the activated carbon. So more adsorption was taking place, right? Temkin isotherm didn't follow that much at room temperature, but higher temperature it followed. We can see the Freundlich isotherm, the 1/n factor. This factor is less than 1. That means the process is favorable. RL is also less than 1, so the process is favorable based on the theory of Langmuir and Freundlich isotherm. The assumption to tell us like this. This is thermodynamic characterization. We have seen that del G is negative, so spontaneous process, del H positive, del S positive. Okay, so entropy, del H positive means it is endothermic process, del G negative is spontaneous process, and here entropy we got positive. That means when the pollutant is going in front of the surface, there is randomly they are absorbing, their chemical structure change and increase the degree of freedom. Okay, so this is some basics theory. This is batch adsorption. Kinetics also we have studied pseudo first order, second order, and Ilovich. So this is, we can see here is the pseudo first order and pseudo second order reaction. We will just see the del Q percentage, which is the error percentage, we can see that our reaction follows pseudo second order. That's why our error is only 1.37, 1.55, 1.71, like this, small error. We did the intraparticle diffusion also, and we did the Ilovich equation also. Ilovich equation also confirm chemical adsorption. Pseudo second order and Ilovich equation also confirm that chemical adsorption process took place, which is irreversible, because del Q in Ilovich equation is also less. So there are several methods for removing organic contaminants, physical, chemical, and biological. So physical method is adsorption is a physical method, precipitation, coagulation, membrane filtration, sonication. Chemical method is ozonization, pentron. Those I am not going elaborately, right? So this is our adsorption process. Coagulation, this is just separation. Agglomerates will be separate. Membrane filtration is a sophisticated method, but it is pressure-based method. Membrane filtration is a pressure-based method, that's why it is costly. And adsorption is less costly and economically friendly method. There is ozonization. We supply ozone to degrade some pollutant. Catalytic wet air oxidation, as I mentioned earlier, we will prepare a catalyst supported by CNT or graphene or activated carbon with metal oxide, and then oxygen gas will be supplied and the pollutant will degrade. Photocatalytic method, we will again use the catalyst, but there will be some UV light. These are different types of microfiltration, ultrafiltration, nanofiltration process, reverse osmosis. These are membrane-based process. My another student has converted activated carbon to CNTs by using CVD method, where he has used the catalyst, iron and cobalt. This is the thing I was mentioning earlier, that this iron and cobalt, after converting to CNTs, he couldn't remove, right? So when he was doing the desalination process, if this CNTs, for his case, there was no leaching. But if there is leaching, then we are introducing secondary pollutants. So we have to be careful there. This was his apparatus setup for membrane fabrication and desalination. This is his stem picture. Okay. This is his desalination setup. I am not going in deep. Why we use activated carbon for CNT growth? Because activated carbon, cheap source, right? That's why we have used for CNT growth. This is his basic methodology. I am not going in deep, right? So this, we have published 2 papers from here. So can be checked these 2 papers. So this is the schematic of this. This is batch adsorption where the carbon is rotating, and when we are using granular activated carbon in the column, then it is column adsorption process. Our lab, we have these types of column adsorption process. Previously, I mentioned that sometimes single process is not enough. That's why we have used granular activated carbon, but we have used some supporting consecutive column, zeolite, limestone, activated carbon again, and zeolite, because we were treating rubber industry wastewater and ethanol industry wastewater, which is a multi-pollutant system. We got some result also, because those multi-pollutant systems, some heavy metal pollutant also there, phenolics also there, some physical pollutant, BOD, COD also we have to adjust. In the single step method, we have to adjust BOD, COD also. That's why we have used 5 consecutive column method. Let us see what happened. Let us see the result. So this was our basic layout. See the result. Untreated sample BOD was, in case of ethanol industry, 1313, which after treatment 535. COD was 2450, it was 1600. This is ethanol industry result. Okay, we can compare rubber industry and ethanol industry result. We can see rubber industry, we got good result by using our consecutive column system. And why consecutive column system? Because activated carbon alone was not sufficient to recover all these things: BOD, COD, ammonia, called nitrogen, iron, zinc, polyaromatic hydrocarbon, phenolics. There are a lot of pollutant present there, right? Physical, chemical, physical and chemical pollutant present there. So we have to target 2 types of pollutant, and there is multi-pollutant system present there. So now green environment using nanocarbon. It is possible if it is leaching free. That's why we have put a question mark, that how carefully we are using it. Nanotechnology is making significant improvement in technologies for protecting the environment. Nanoscale devices are also being used. Someday we may be able to prevent pollution with the help of nanotechnology, but we have to be careful. We might not increase secondary pollutant. Or maybe on the other hand, nanotechnology's unique characteristics may also lead to unforeseen environmental problems. So we have to be careful for this. Okay. So Toxic waste cleanup is very important in the riverside or anywhere else. It can be physical pollutant, it can be chemical pollutant. So we have to be careful for throwing all the rubbish into the riverside or into the seaside. We have to be very careful, especially in Malaysia. Pollution is a serious issue. River pollution is a serious issue. I am working on some project like this. So we have to be careful. According to Professor Joel Pederson, Environmental Chemistry and Technology Program, medicine, there are three main factors affecting the impact of nanoparticle in environment. For a given amount of matter, there is a great deal of more surface area when particles are smaller. Of course, when nanoparticles are smaller, there will be more reaction and there will be more efficient removal process to some extent. But sometimes in case of adsorption, desorption also can go faster in nanotype material. A second concern, that is core material of the nanoparticles can be toxic, because when we synthesize nanoparticle, there are some core materials, so those can be toxic, because inside the environment when it will go, the outer layer can be broken. So lastly, the environmental itself affect the toxicity and fate of the nanoparticles. We don't know. There is no elaborate studies for all the nanoparticles fate in environment. We don't know. So there is some unforeseen effect also, right? So we have to be careful. Of course, nanoparticles give us more result because volume to surface area ratio is more. We can see from this cube that the smaller cube has volume to surface area ratio 3:1, but the larger cube has ratio 0.6:1, right? So which one will be faster reaction? Obviously the nanoparticle. I am not disagreeing that adsorption process will be faster by using nanoparticles. But I am concerned that desorption will also take place. Can it hold it for a long time? The pollutant can be hold it for a long time, or after 10 minutes it can come back. Because in my lab I have seen, I have used CNTs, the pollutant removed, bisphenol removed, but after 15 minutes it came back again into the solution by using CNTs. But activated carbon I used, okay, it took slowly, within 1 hour it took the bisphenol same concentration, but it didn't give it back. So which one we will suggest as a best, as a winner? Activated carbon, right? So this depends on scenario to scenario also, pollutant type also, atmosphere also, right? So that is the thing. Of course, nanocarbon is better for membrane separation process, because it can prevent biofouling of the membrane. If nanocarbon is present in membrane matrix, then virus bacteria cannot form, virus bacteria cannot accumulate over the membrane surface. Automatically, it will degrade the bacterial membrane or virus membrane, right? So biofouling can be prevented, right? So in that case, nanocarbon is better. But obviously, there also, since membrane separation process is a pressure-based process, we have to check that no nanocarbon should be leached out from the membrane matrix. So we have to concern about health, safety, environmental concern regarding the nanoparticle when we are using, because we can inhale this nanoparticle, Darman contact, we can take this nanoparticle, we can ingest also. So that's why nanotoxicology is now the new subject coming into the area. So for water treatment, when you are using nanoparticles, we have to be careful. That is my concern. We can use nanoparticle, but very carefully. That is the thing. And not too much amount. Whatever needed, small amount is sufficient for nanoparticles to react and remove the pollutant. Sometimes the students, what they do, they think that we use more nanoparticles, then quickly the pollutant will remove and we will finish the reaction and our thesis will be completed. This is completely wrong. As much as possible, use the less material nanoparticles and try to remove 100%. And later on, see how you can separate it. This is the main thing. So we have to revisit, and we need the evaluation before using the nanoparticles up to a greater scale. How we can minimize the hazard and high risk exposure to high risk of nanoparticles. Evaluate present risk management plans for all types of nanoparticles. We don't know for all types of nanoparticles, right? I have discussed only here for carbon, but there are a lot of types of nanoparticles. We don't know. There are a lot of organic nanoparticles also. We don't know that what is their hazardous aspects or what is their effect on biological organ, right? So those, if we know, then we can use it carefully, right? So this is, so where we are today for nanotechnology studies. Limited number of nanomaterials have been evaluated to date for their toxicity effect. Mechanism of potential toxicity of nanoparticles, specific nanoparticles properties, specific types, what is their fate in environment, surface characteristics, and how their toxicity level will be increase or decrease in the environment, how they will degrade in the environment. We don't know the mechanism clearly. No specific regulation has been maintained until now. So thanks a lot. I trust and hope that you will take home further information on how to foster and use nanotechnology, nanomaterials for green environment, but up to which extent. Please make it in the mind that we can use nanoparticles. Of course, we will use in modified version. We will use, but with care and with lot of responsibilities, and disperse this carefully in the environment so that it might not create secondary pollution in environment. Thank you. This is all from Dr. Zairazaman Chaudhary. If there is any question, please kindly ask. If there is any question, I will be glad to answer.
Thank you very much, Dr. Zaira, for addressing this very interesting topic. Ladies and gentlemen, now we come to Q&A sections. I will read the questions from the chat box. If you have, please tab it in the chat box now. Let us read the first question. The question from Owen Daniel is anhydrous calcium chloride considered an absorbent? Dr. Zaira?
Anhydrous calcium chloride can absorb, but some of the material, not all. We cannot tell it as, don't tell it as ideal adsorbent material, because there is chlorine also present. So we avoid to use anhydrous calcium chloride because chlorine is present there, which is not good for water also. We can use, but let's say in ball milling time, some process we use. Ball milling time, when we are making activated carbon to nanocarbon, that moment we are using anhydrous calcium chloride to just to absorb the moisture, okay? Not for pollutant purification in larger scale, we use calcium chloride. We don't prefer.
All right, thank you. We have another question from Afrin Jahan. While carbon preparation does carbon dioxide gas flow and nitrogen gas flow provide the same yield?
No, no. Nitrogen gas or argon gas is used for inert atmosphere creation. And carbon dioxide gas is used as an activating gas in presence of any types of base. Let's say we have activated our carbon with potassium hydroxide or sodium hydroxide or lithium hydroxide. Any types of hydroxide is used for activation, chemical agent is used. Then we will flow carbon dioxide. After flowing the nitrogen for 10 minutes, we will use carbon dioxide for water shift reaction. This is a special kind of reaction, water shift reaction, where potassium or sodium, any types of metal, will go for intercalation reaction. Because activated carbon is graphite-like layers, right? So what it will do, this potassium will run so fast inside the pyrolysis apparatus, it will extend the distance between two graphite layer or three graphite layer. So the internal surface area, which we call basal plane of carbon, we call it basal plane of carbon, that will be increased, and ultimately our surface area will be increased. This is a special kind of reaction in presence of alkali metal oxide, metal hydroxide. We call it water shift reaction. Then we use carbon dioxide gas. It is an activating gas in that case. And nitrogen and argon always we have to use before any reaction starting in pyrolysis apparatus to evacuate oxygen, otherwise ash will form. We want to reduce this ash, that is the thing in carbon.
Thank you, Dr. Zaira. Now we have reached at the end of this section. Thank you for your participation. If you would like to get the certificates of participation, please scan this QR code. You may scan this QR code for the certificates of participation. For our next event, tomorrow we have virtual demonstrations on graphene oxide synthesis by using the simplified Hammers method to be delivered by Dr. Malinda Raman tomorrow, July 26, 10 a.m. to 11 a.m. See you guys tomorrow. Hope to see you again. Thank you.
Thank you.
Bye from now.
Thank you. Thank you. Thanks a lot.